On this last video for improper integrals, let's go ahead and talk about what is called the comparison test for integrals. So if we happen to have two continuous functions, we'll call them f of x and g of x, such that f of x is greater than or equal to g of x, which is greater than or equal to 0 for all x greater than or equal to a. So if you look down here at this image, this is an image describing the relationship between these two functions. So g of x is always smaller than f of x. They are both positive functions, and we are looking at this from x is greater than or equal to a. Then, if we consider the integral from a to infinity of f of x, if the bigger function converges, then the function that is always below it must also converge. If we think about this in terms of area, what we're doing is we're thinking of if we have convergence of that bigger function, that is telling us that the area from a to infinity under f of x to the x-axis is finite. Well, then, of course, any other area trapped underneath it would also have to be finite. And so if the larger function, so this is when we say f of x, this is the bigger function. If the bigger function converges, then the smaller function must also converge. And if we have a different result, suppose that the smaller function now, g of x, if g of x diverges, if the smaller function diverges, does not have a limit when we look at the limit as t is going to infinity of that upper bound. If we have divergence, then the larger function must also diverge. So again, here we're looking at the smaller function. If we have divergence, if that is approaching infinity, again, in the context of if we're thinking of this in terms of area for these positive functions, if this function underneath has trapped an infinite amount of area, an infinite number or an infinite amount of area from itself to the x-axis, then any function larger than that must also be trapping an infinite number of area. So this is the bigger function. So again, we can think of those in terms of areas. So if we interpret the ideas above in terms of area, we can summarize it in this way. And I wrote it out here as well. So how do we use this? Well, we use this when we are doing integrals and we want just the idea of whether the integral converges or diverges, because this won't tell us what we're comparing our integral to. It won't tell us what that original integral is converging to. It will just give us convergence. It's a comparison, not equality here. But it will be a useful tool if we just need to determine convergence or divergence. So we're going to look at two examples, but before we do, let me get on the screen a little proof, a little result that we proved at the beginning of this section. Okay, so let's determine if these two integrals converge or diverge using comparison. So we'll use that comparison test. And we're going to use the fact that the integral from 1 to infinity of 1 over x to the p dx will converge for p is greater than 1 and will diverge if the p's, the powers on x, are less than or equal to 1. So we proved that in the very first video on this topic of improper integration when we were practicing with some basic integrals, but now we're going to use it in comparison. So these are not such basic integrals, but on this first one, when I take a look, let's zoom in here a little bit. When I take a look at this, the first thing I notice is that I have 2 plus e to the negative x. And so my little thought bubble here is that this gets really small because it's 1 over e to the x as x approaches infinity. So this little piece in the numerator is going to be getting really, really small. So what I'm doing here is I'm going to go ahead and think, when I'm thinking about what am I going to compare this to, what I do is I think about 2 over x, because that 1 over e to the x, or e to the negative x, gets really, really small as we approach infinity. And remember, we're approaching infinity. So the integral from 1 to infinity of 2 over x dx, if that's what I'm going to be thinking about, that's 2 times integral from 1 over infinity of 1 over x dx. And I'm not going to go through the whole proof on that because we did prove that, actually, that exact one, the integral from 1 to infinity of 1 over x on the first video. I'm not going to prove that. It was part of our process when we were actually proving this result we have up in the upper corner here. And the power is 1. So I do know that this diverges since p is equal to 1. So I'm comparing my integral to a diverging integral. That's what I want to do here. So I have to set this up. So to do the comparison test, so to use comparison, we have to set up an integral, an inequality to compare the two integrals. To compare two integrals. So I need to set up an inequality. The first thing I do actually is I think about what I want to compare it to. That'll help guide my work in setting up that inequality. So let's go ahead. We're going to set up the inequality. We know that 2 is greater than 0, and that is also less than 2 plus e to the negative x. So we know 2 is bigger than 0, and we know that 2 plus e to the negative x is bigger than 2. So we can start off by setting that inequality. We do know that. I will add in why we know that. We talked a little bit about it up here, but that is because e to the negative x is always greater than 0. An exponential function is always greater than 0. That is true for all x. So that's why I can make that statement. Then, if x is greater than 1, that means that x is positive. And if it's greater than 1, I can divide everything here by x. And it will keep the inequality as it is. If x is greater than 1 and it is positive, it won't flip the inequalities. And we'll end up with a result that 0 is less than, we know this, we know we're working with positive functions. So 0 is less than, or we could say 2 over x is greater than 0. And at the same time, 2 plus e to the negative x is over x is greater than 2 over x. And that's the inequality that we need, because this is our smaller function, this is our larger function, and we already know that the smaller function is diverging. So we can make a conclusion. We can say, therefore, by comparison, since the integral of 2 over x from 1 to infinity dx is equal to 2 times integral from 1 to infinity of 1 over x dx diverges by p equaling 1, then the integral from 1 to infinity of 2 plus e to the negative x over x dx must also diverge. And that's my conclusion. So we start off by determining what is it that we want to compare it to. So we thought about how that function was built, how that function was set up in the numerator there with just a 2 plus e to the negative x. Then we built the inequality so that we could compare to a diverging, in this case, diverging integral, and then stated the comparison test result. So let's take a look at one more. Let's look at this guy. If we've got our second example, if we're integrating from 1 to infinity of x over the square root of 1 plus x to the 6 dx. So same idea on this one. As we're going to infinity, I'm looking at this 1 right here, and this 1 is going to become really small as the x's grow without bound. So what I'm going to do is I'm going to think about what to compare to. What function to compare this to. And if I do that, what I can do is I could think about, well, what is 1 over infinity if I get rid of that 1? What does that look like? Because that 1 becomes really small in comparison to the x's as x grow without bound approach infinity. So what would the integral of x over just the square root of x to the 6th be doing? What kind of behavior would that have? Well, from 1 to infinity of x over, that would become x to the 3rd, but that just becomes x over x to the 3rd. That's just 1 over x squared dx. And we actually know from that result, let's get that result up on the page. Let's copy that down here. So there we go. I copied down our result from previous. So 1 over x squared, well, that's a p-value. That's a p-value that is greater than 1. So not only do we know that this converges, we would know exactly what this converges to. This converges to 1 over 2 minus 1, which is 1. So this converges. This has a finite, if we want to think in terms of area, this function, it is always positive, and it has a finite amount of area trapped underneath the function to the x-axis from 1 to infinity. So how can we use that to go back to our original and use comparison to determine if it converges or diverges? So now we need to set up the inequality, but we have an idea of what it's going to do. We have an idea that it's going to be compared to 1 over x squared, and that function's integral converges. So comparison test, so if we want to use a comparison test, we have to set up the inequality. But we got to do a little bit of back work, a little bit of inequalation. That's funny. Inequality. I was talking and writing. Okay, so we know what we want to compare it to, so now let's go ahead and get it set up. So first thing that we want to think about is this. Let's look at the denominators to start here. And we already talked a little bit about this, but the square root of 1 plus x to the 6th, that is bigger than, just a little bit bigger, because it has that 1 as x is approaching infinity, but it is certainly bigger than the square root of x to the 6th. And the square root of x to the 6th, of course, reduces down. This is equality, reduces down to x cubed. So when I flip these inequalities, what's going to happen, or when I flip the inequalities, when I reciprocate both sides of the inequality will flip. So since that is larger, when I take 1 divided by the larger quantity, that will now be less than 1 over the smaller quantity. So we reciprocated, reciprocated, which then changes those inequalities. You could have started with the second inequality I have here, but sometimes I think it can help to think about the denominators and if they are larger or smaller. All right, then I can do the same thing actually that I did on the previous one. I can multiply through, since x is greater than 1, which also means x is positive. There are two things implied there. I always like to say that because we do have to be careful when we're multiplying inequalities by negative values. But it's also important that x is greater than 1. So we're going to multiply through by x. What we should add in here, I'm going to add it in red. This is implied because 1 plus x to an even power will always be positive, and then when we take the square root. But we are staying positive here. All of these functions we're talking about here are positive. They are greater than 0. So x over the square root of 1 plus x to the 6th is less than x over the square root of x to the 6th, which of course is just x over x to the 3rd. I realize here I carried the 6 over, not the 3. X over x cubed, which is 1 over x squared. And so what we have just shown, therefore, that our function, and I did some of the algebra there as I was working through that inequality, but the inequality boils down to this, that the function we're working with is smaller than 1 over, I keep doing that, I keep wanting to keep my 6, is smaller than 1 over x squared. This is the smaller function. And we know that the bigger function converges. We already showed that. So if the bigger function is converging, there it is up at the top, what we can say by comparison, therefore, by comparison, if the bigger function is converging, then the smaller one must also converge. So the integral from 1 to infinity of x over 1 plus x to the 6th dx must converge since the integral from 1 to infinity of 1 over x squared dx converges by p equaling 2. And that's our result. So we can use that proof that we did at the very beginning of this section. We can use that proof in this way with comparison, and it is nice. That is a useful, I'll go ahead and let's give it a little bubble here. That is a useful proof that we did when using comparison. This becomes especially useful for comparisons. And that wraps up our section on improper integration.